Mom, were you saying something to me?
Yes, Aisha, am I audible to you?
Yeah, Mom, I'm so sorry. I wasn't responding.
Okay, no problem. See, we in the last class we started with the kinematics of the circular motion. Okay,
Yeah.
so that we have completed more or less. The whole entire portion was over. The derivations we did and the two questions we have completed. Now see, I want to start the next topic, that is torque. So basically, did I discuss torque with you?
No, Mom.
Torque was left. No? Yeah. So basically, see, whatever the force is doing in rotational motion, that is the same work done by the torque. Means force is there in your linear motion and torque is there in your rotation motion. So moment of force about the axis of rotation is known as the torque. So here we have a position vector, and remember here, let me tell you a few things. This is the axis, this is the x-axis, this is the y-axis. Now, from the origin to a point P, a force is applied, let's say some force F, and a position vector R has been applied. So, when the force is applied here, the position vector is R. Formula is very simple for the torque. Torque basically uses, this is the symbol for the torque, tau. The symbol is called as tau, and this is the torque. So, this is R perpendicular cross the force. R perpendicular means you only have to consider the perpendicular component. This means, like, if I have, let's say this is the force, and this is the entire line of action of the force. Okay, this is the entire line of action of the force. Now my radius is lying at some angle theta, that is not 90 degree. So you can drop a perpendicular to this line of force wherever needed. If this is the line of force, you drop a perpendicular over here. This is the line of force. So this is the line of force where the perpendicular will be dropped. So that is the R perpendicular. And wherever any question when you solve this has to be kept in mind that you will be using the R perpendicular for the solving part. You can never use any radius. If any radius is provided to you, you are going to take its component, you are going to make the perpendicular. Like in this triangle, if we take sine theta, that is R perpendicular divided by hypotenuse. Yes.
Can you explain how do you make the perpendicular again?
See, if I have a force, let's say this is a point and this is the force. And from the origin, this is the separation R. So torque says R cross F, so I should have multiplied these two. Now, usually you will get them perpendicular, but what if R is not perpendicular to the force like this case? So what you do, wherever the force's line of action is, line of action means the line at which the force is acting, you extend that. And from the radius, from the position vector, you drop up the perpendicular. Then you use this perpendicular in the calculation. To find out this perpendicular will be your task. Now got it?
So the force will be same, just the
Force will be
perpendicular.
the same. Yes, yes, yes. Force, there is no change in the force and no condition for the force. But the condition is only for the radius. That is the perpendicular vector. Okay, so
Okay, Mom.
sine theta
Thank
is
you.
R perpendicular by R. So from here, O and P, if from this triangle, if we write sine theta, that is the perpendicular by hypotenuse. It is R perpendicular by R. So from here, we can say R perpendicular is R sine theta. Torque is already R cross F. And whenever we have the cross product, when we open it, this is RF sine theta. This is RF sine theta. This is the torque. So torque is basically the rotational analog of force. And what is this theta? This is the theta between the radius and the force. Okay, so you can simply say R perpendicular is what? It's the perpendicular distance between the axis of rotation and the line of action. Means if a force is acting over here in this way, and I have some position vector like this, so it's fine. Both of them are making an angle of 90 degree. This is force, this is position vector. But if I have a force acting like this, which is F, and the radius is acting like this at some other angle other than 90. So we take the line of action of force and we take this perpendicular distance. And this R perpendicular will be under consideration, not this one. So our perpendicular is important. Perpendicular distance between the axis of rotation and the line of action of the force. Write it from here.
Okay. Done now. Done, ma'am. Done, ma'am.
Okay. See, regarding the torque, you will always have any axis of rotation. One axis of rotation will always be there. Let's say this is your main axis. This is the axis which is present, and here a force has been applied like this. So when the force is perpendicular, see, means angle between the radius and the position, that is 90 degree, when your theta is given as 90 degree. Then see, torque will be sine 90 is 1. So we will directly get torque is equal to RF. That's it. You don't have any other thing. So this is the maximum torque that is occurred. You can relate it with some daily life example because torque is based on rotation. Okay, the door actually rotates. Door doesn't move back and forth when we open it. Door is fixed on the hinge. So yeah, so door basically rotates. So whenever we have to open the door, we'll have to apply a perpendicular force to it to open it. And with that, the door opens. So this is what is meant by the maximum torque applied. Second is, and I'll tell you one more thing, how can it be increased? If theta is 0 degree, your torque will be 0. If theta is 180 degree, third case, the torque will be 0. Here, because sine 0 degree or 180 degree is used, that's why it is 0. Now, one more thing before we begin angular momentum.
Ma'am, what's sine 180 degree?
0. That's also 0.
Oh, okay.
Okay, so because of that, also the torque that is applied is 0. Now, this is the torque. If you have to give a maximum torque, to increase the torque, to increase the torque, you can increase the R perpendicular also. You can increase R perpendicular. So see, whenever a door is there, the good example is of a door. See, this is how a door is put. This side is hinged. This is the fixed hinge. So this is this side which is fixed. So this is known as the axis. This fixed one will be known as the axis of rotation. This edge one, this fixed one will be the axis of the rotation. This one. Now, if I increase this R perpendicular, I'll get a maximum value of the torque. So see, that's why the handles of the doors, they are always connected here across the free edge. This is the free edge. So across the free edge, the handles are connected. We never have the handles near the fixed edge. Have you ever seen a door where the handle is very closer to the wall edge? No, it's always towards the edge. Free end, it's always towards the free end because that increases the radius and it becomes very easy to open the door. Okay, so this is one example. One more thing, we did a relationship in case of the circular motion. See here also you should remember whenever you calculate work done, it will be tau d theta integrating theta 1 to theta 2, because we are already done with work done, that is f dot dx integrating it from x1 to x2. This is tau d theta from theta 1 to theta 2, like this. Now one more thing, if I have work done as equal to tau d theta and I divide both the terms with dt. So look, work done by time will be
Can
equal
you
to
explain
power.
this work done again?
Yeah, I'll explain. See, for work done, actually in work energy in power is equal to force dot dx, wherever the force is variable from x1 to x2. We have done this, remember?
Yeah.
If our force is variable. If you have torque, instead of force, you will get torque. And instead of dx, you will get d theta, because all these are rotational terms. Means basically, I want to say that all the rotational component terms will come. Okay, whatever rotational. Angle, the displacement, linear displacement is there. Here you will have the angular displacement. Like this, all the entirely this will be based on the rotational part. So your linear force will become torque, linear displacement will become linear angular displacement. So instead of x, we'll use theta. Instead of force, we'll use the torque. This part is clear?
Yeah, ma'am.
See, work done is basically tau d theta. If I divide both the terms with dt, I get one more relation. Work done by time is power. Torque as it is d theta over dt. If you remember, can you tell me what is d theta over dt?
Uh,
Rate of change of angular
omega.
displacement is
Omega.
omega. Very good. Angular velocity. So tau omega. This is one more relation that we'll be using. Got it?
Yeah, ma'am. I did.
Okay. So let's practice few numericals based on this. Please write it.
Done, ma'am. Done, mom. I'm sorry, I keep forgetting I'm the only one here.
No, actually, that's not a problem. It's okay. Aisha, we'll practice few questions based on torque. Then we'll move on to this angular momentum. Okay.
Okay, mom.
Okay. See, this says a force is acting on a particle and the separation from the origin is given. You have to calculate the torque. So torque is basically R cross F. So that means this is the cross product over here. Now, R is given as I cap plus J cap minus K cap, while the force is given as 7 I cap minus 3 J cap minus 5 K cap. So we'll take I cap, J cap, K cap, I cap. See, for the radius, we'll first put, we can never write F cross R because the formula is only R cross F. So R will always come first, then the force will come. So this is 1, this is 1, this is minus 1, while the force is 7, minus 3, and minus 5. Now, see, here we'll apply. For I cap, we'll multiply 1 into minus 5 plus, sorry, minus. Basically, we are actually cutting this and this. This multiplied to this multiplied to this. So minus 3 into minus 1. This much is for the I cap. Now for the J cap, we put a negative sign in advance and J cap is cut. So these two are multiplied minus these two. 1 into minus 5 minus 7 into minus 1. This is J cap. And then we have the K cap. I cap, J cap, K cap. This is the K cap present. So this gets multiplied to this. So we'll have plus for J cap, K cap, 1 into minus 3 plus 7 into 1. That is, oh yes, this is minus, correct. This is minus. So our answer will be, this is minus 5 here. Minus 3 into minus 1 is 3. And here a minus sign. So minus 5 minus 3, that is minus 8 I cap. This is minus 5 here. This is minus 7. Minus 7 minus 7 means minus 7 minus, that is plus 7. 7 minus 5 over here 2. And this sign minus 2 j cap. This is minus 3, this is minus 7. So minus 4 k cap. Now unit Newton meter. See, unit of torque you haven't written, no? Okay. Unit is Newton meter and the direction is given by a right hand thumb rule. But right hand thumb rule you don't need to apply every time. We'll see according to the questions it will be solved. You write it, few more questions, let's practice. One or two more we'll practice. First write it.
Okay, ma'am. Mom, wasn't right hand thumb rule something about current?
Current is there, right hand thumb rule is basically about directions. So for different things directions are present. For current is there, for your magnetic field is there, for torque it's there, for many things you have. I think you must have done Fleming's left hand rule and all also in your lower
Yeah.
class. Yeah, so those are actually used. This is just like a regular rule, it's like a law. But anyways,
Oh,
that is used for any quantity. But for every quantity you have fixed pattern. Okay.
okay, ma'am. Done, ma'am. Yeah, mom.
All right. So, yes, class. Now we have angular momentum. Let me discuss angular momentum first. Then the torque angular momentum combined questions we can practice, which is the concept of equilibrium and coupling of forces. So, angular momentum, linear momentum, you have already studied. Linear momentum was the amount of motion in the body. That was the mass, product of mass and velocity. We have discussed it was represented with M. So, mass with P, which was mass into the velocity. So moment of linear momentum, basically, moment of linear momentum means the rotational analog of the linear momentum. I'll write it here. Rotational analog of linear momentum. This is linear momentum. Basically, whatever work the linear momentum is doing in translation, that same work is being done by the angular momentum. So see, what you do, you convert things. Here you have a concept that is known as moment of inertia. We'll be applying that. Moment of inertia is very important, but moment of inertia I'll be discussing once we are done with moment of inertia. First, I'll introduce you to the topic moment of inertia, and then we'll discuss further. Right now, how can you relate is, right now you should know that angular momentum is represented by the symbol L. This is the symbol for it. And this is R cross P. The way torque was R cross F, rotational force was R times the linear force. Similarly, this also, this is your angular momentum. L is basically the angular momentum. R is the position vector, still the perpendicular distance. This is the position vector. While this P, this is your linear momentum, which you have already studied. Linear momentum. C. If we talk about the force also, the torque. How did we write torque? We wrote torque as R cross F. Means the rotational part, torque, this was the position vector, and this was the linear force. Similarly, here also it is equal to R cross P. There is one more formula based on this, but for that we need the moment of inertia concept. So here also likewise we have drawn for the force and the torque, we will be drawing the same thing for the angular momentum. So point here, perpendicular. Now it's an axial vector. Axial vector means wherever is the axis. Let's say this is the axis. Let's say this is the axis. Here the direction of that vector will be associated. That will come through understanding the questions and all. So what is angular momentum? Here axial vector along its direction is means it's an axial vector. Two kinds of vectors are there. Axial vectors are those vectors, those are basically along the axis of rotation. Like if I have my axis of rotation here and some force is being applied here, and this is, so I get torque, which is again an axial vector. So when I talk about axial vectors, they act only in rotation. Got it?
Yeah, mom. Mom, so torque and angular momentum are related.
Torque.
Torque and angular momentum, are they related?
These two.
Yeah.
Yeah, they are related, but they are related through some laws that I'll tell you later. Like linear momentum and force are related, so they are also related. Like let me tell you here itself, since you have asked. We know force is equal to what? Momentum by time. So similarly here also, torque is equal to angular momentum by time. So this we'll be discussing in the conservation of angular momentum. Fine till here?
Okay. Yeah, got it.
Okay, please write it.
Mom, is that L a normal L or is it a symbol?
No, this is a normal L. L to represent it. But all of these are vectors.
Oh,
This
what's the
is
name of
also a vector. Name of this?
the torque symbol?
Torque, tau. Tau.
Okay, thank you.
This symbol is tau, which is written like this, which stands for torque.
Thank you, mom. Done, ma'am. Ma'am, I'll play acid and come back.
Yes, Aisha?
Can I pray acid and come back?
Yes, yes, come.
Thank you, ma'am.
Okay, let's discuss moment of inertia also. Moment of inertia is basically whatever is the work done by, or you can say whatever mass does in the linear motion. When whatever mass is doing in the linear motion, that same work is done by the moment of inertia in the rotational motion. This is in the rotational motion. Because see, mass is for the translational part, okay? And moment of inertia is for the rotation part. Now the formula of moment of inertia is very simple, very easy. If let's say this is some body is present over here. Let's say this is the axis of rotation of the body. So from the axis to the point of calculation, wherever you have, you take out the radius. And the formula is basically moment of inertia is represented as I. The formula is mr square, where I is the moment of inertia, moment of inertia, m is the mass of the body, and r is the radius vector. So this is still this moment of inertia. This is the formula is very simple, which is mr square. Now see, SI unit will be mass is kg, radius square is meter square. This becomes the SI unit. The CGS unit of it is gram centimeter square. These two are there. Write it, then let's see some questions.
Can you scroll up after the formula of the angular moment? Yeah.
Yes, this part, no? Yeah, write it, then let me know. I'll scroll it down.
I took a screenshot, man. You can scroll. Done, ma'am.
Okay, see, let's see this question. That is, calculate the moment of inertia of a ring about an axis perpendicular to the plane of the ring. See, class Shanika. If this is a ring, this is though it's a disk, but if it's a ring, axis means it will be passing through it. So perpendicular to the plane. This is the plane. So perpendicular to the plane will be this. So it's like that your ring is put like this, and the axis is present. This is the axis of rotation. The axis of rotation. So if it's a ring, let's say its radius must be something. Let's say the radius is r. Now let's apply the moment of inertia. Moment of inertia is equal to mr square. That's it. That is the answer to this question also. Mass of the ring and the radius square. That's it. Now write this first and let's see some more questions.
Done, ma'am.
Okay, see, so it says calculate moment of inertia of a rod about an axis passing through its center and perpendicular to its length. Now understand this. Let's say there's a rod. This is the rod, and the axis is perpendicular to its center and perpendicular. Means this is the center and perpendicular to it. So through its center and perpendicular. This will become your axis. Now axis will be treated as if this is the origin. So what will happen? This side of it will be, see, if let's say the total length was some L and this is through the center. So this part will be how much? This will be L by 2 and this will be L by 2. Half of it, this will be L by 2, this will be L by 2. Now, this is treated as the origin. You take this side as minus L by 2, you treat this as plus L by 2 because this is your axis, which is the axis of rotation. Now, in order to calculate this, to solve this, what we will do, we will choose a very, very small element. A very small element we will take that is having the length dx, whose mass is dm. And we'll calculate what is the value of this dm. Now, integration, when you have it in terms of the variables, and you see it is differing, it is varying with quantities. Then instead of using mr square, use integral of mr square from x1 to x2 like. So here the moment of inertia will be integral of dmx square. What?
Can you repeat when do we use the integral?
Yes, integration when you have something variable. Like I have chosen a very small element dx. So let's say I'll write it here. Consider a small element of the rod of length dx and mass dm. Okay, length is dx and mass is dm. In those cases you don't have to use mr square, you integrate mr square. You use the variable form. Now this will be integrated from minus L by 2 to plus L by 2. This is how it will be integrated. So when we use moment of inertia, okay, we need to find out the value of dm. Like this we cannot integrate because this is length and here we have dm. Of course, mass has to be changed. Now see, the length of the rod is L, mass is m. Let's say mass is m. So mass of L length of rod is equal to capital M. What is mass per unit length? From here, mass per unit length. It will be M by L. Okay, so if you a mass per unit length means you know the mass of unit length, 1 meter, you know, so you'll be able to calculate anything. Now, what's the length that we have? We have the length dx. Mass of dx length of rod will be m by L into dx. Now this is what? This is dm. Mass of dx, length of rod will be dm. That we have got all the values of dm. Now we will put it. So I is equal to moment of inertia is equal to, instead of dm we will get m by L x dx, x square actually. X square is here. This is x square. Dm is m by L into x, and this your x square is already present. Integrating from minus L by 2 to plus L by 2. First tell me till here, is it clear?
Yeah, ma'am.
Okay. Now see. Now we just have to solve. M by L will be taken out. X square will be written as x cube by 3 from minus L by 2 to plus L by 2. So m by 3L. We'll put the upper limit first, that is L by 2 whole cube minus, now the lower limit, minus L by 2 whole cube. Okay, this is m by 3L that we have. L by 2 whole cube and minus L by 2 whole cube. Let's solve this further. Let's just simplify it a bit. This will be m by 3L. Now L cube by 2 is L cube by 8. And what is minus L cube by 8t? It's actually like minus L by 2 into minus L by 2 into minus L by 2. The minus into minus will be plus, but plus into minus is again minus. So you will still get this as negative. When you solve this whole part minus this minus L by cube, this will still be a minus L cube by this is 8. That is equal to plus m by 3L into this will be L cube plus L cube by 8, which is m by 3L into 2L cube by 8. Here 2 gets cancelled. This is 4. L, this becomes square. So finally, the moment of inertia of the rod about an axis which is perpendicular to its center and passing through the center and perpendicular to its surface is ml square by 12. Now you need to remember this also. For more figures, I'll tell you. This you need to remember. So here the moment of inertia was ml square by 12. Got it?
Yes, mom.
Okay, please write.
Mom, how do we remember this formula? Like, how will this question be framed?
This is actually a derivation, Aisha. This one, no, this one is actually a derivation which comes in the exam. That's why it's in the form of a question which I have written, but it's actually a derivation
Oh, derivation
of the moment of inertia of a rod. The axis is passing through its center and perpendicular to its center. If the axis was at the edge, means here. If the axis, this blue axis, if it was here, the answer would have been ml square by 3. So that's a different one, but which you don't have to actually focus on, and it can be calculated in the similar manner. It will be then integrated from 0 to L by 2, 0 to L, that's it. It will be ml square by 2. Anyways, this is a derivation when the axis is here, exactly for this position, okay?
Okay, mom, got it. Thank you. Done, mom. Done, ma'am. Ma'am, in the second step, in the second part, we just L by 2 and minus L by 2, we just raise the powers to 3.
Where?
In the second step, the second
Uh,
part, L
uh,
by 2 and minus L by 2, we just raise their powers to 3 instead of x.
yes, we put the limits, no? X cube is there.
Yeah.
So
Oh, okay,
upper
okay.
limit and then lower limit, okay?
Okay. So what's the minus 4 over there then?
This minus L by 2.
No, minus 4. After.
Minus
Yeah, this one.
minus 4?
Yeah,
Where?
you've written just below your cursor.
This is M by 3L.
No, before that. Uh,
1. No, this is
yeah.
L by 2. L by 2. Minus L by 2.
Oh,
Okay.
okay. Done, ma'am. Done, ma'am.
Okay, Aisha. Then I'll stop here. In the next week, we'll complete. Okay.